Hello, I am Jarek Frankik and this is the M3 Maths test in Vector Algebra for the CI4500 Games Science module in Kingston University London. In a space combat game, you are controlling a space fighter in a galactic battle. Your initial position is minus 1110. The best thing we can do with this is to take a sticky note and make some simple drawings. So this will be our coordinate system. Alright, my initial position is minus 1110, so it will be somewhere, say, here. This is my position and this is minus 1110. You are flying straight on with constant velocity and you know that you will pass by a beacon at the position 13 minus 8. So the beacon is somewhere here. And its coordinates 13 minus 8. And I'm flying straight line, so it will be something like this, in this direction. Alright. In 15 seconds, so let's make a note. Time equals 50 seconds. Your enemy initial position is 3023. Oh, to keep the scale I would have to go out of this yellow sticky note, but never mind, it's just a sketch, so I will put here, it doesn't have to be exactly to the scale. It's important that I have all the coordinates put here in this drawing. 3023, he's moving in the direction that is perpendicular to your direction. Perpendicular, this is my direction, so enemy's direction will be something like this, and this is of course a right angle. Twice as fast as you, reducing the distance between his and your spaceship. So if it is reducing, this means that he is flying this way. Alright, so we have a small drawing, and now let's have a look at the question number 1. Calculate the initial distance between the ship and the beacon. Alright, so distance, ship, beacon. I will stick my drawing here and let's think about how to calculate this. This is the distance between my current position and the beacon. First thing that I need to calculate is the displacement vector. So this is the vector that is sitting here at my position and it's pointing to the beacon. So this is the beginning, this is the end. This will also be the relational coordinate of the beacon in relation to my current position. So my displacement vector will be coordinates of the end of this arrow. So these are coordinates of the beacon, 13 minus 8, minus my current coordinates, minus 10, 10. And if you only make no mistake with negative numbers, okay, you have to be very careful about negative numbers, that should be reasonably easy to do. Okay, so 13 minus minus 11. Minus and minus gives plus, so it's 13 plus 11. It gives us 24. Minus 8 minus 10. Minus 8 minus 10, it will be going down even farther into the domain of negative numbers, so minus 8 minus 10 is minus 18. And for the magnitude of the vector, we have this well-known formula here. So my magnitude of d is a square root of 24 squared plus minus 18 squared. But I know that square of a negative number is always positive and actually equal to the square of the corresponding positive number. So I won't even copy this negative sign here. I will simply put here 18 square. And this is the first of the common mistakes you were doing during this test. Some people just consider that a square root of negative number is negative. Also, quite often you made this mistake with the calculator, unless you provide some bracketing. This type of calculation, 24 squared plus minus 18 squared, can be considered by the calculator as something like this, and we end up with 24 squared minus 18 squared, which would lead us to a wrong result. So it's good to notice that minus 18 squared is the same as 18 squared, and run this calculation like this. The square root ends here, so calculating this further, 24 squared is 576 plus 18 squared is 324. These two numbers added together give 900, and the square root of 900 is 30. We have the first answer, which I will add to this sheet, 30. Question number 2. Calculate your speed, normalized direction and velocity vector. How to calculate the first thing on this list, speed. We already know the distance, we also know the time. And a very simple calculation for the speed is the distance divided by time. Our distance calculated in the previous point was 30, and time of travel is 15 seconds. Therefore this is 2 units per second. Direction is the normalized vector of your motion, of your displacement. Our displacement vector was calculated in the previous point, and I will just quickly check. It was 24 minus 18. Therefore normalized direction vector is 24 minus 18 vector divided by its magnitude. Its magnitude is once again something that we have already calculated. Its magnitude is the distance shipped to beacon, which we calculated previously. It's 30. So this is a vector that consists of values 24 over 30 minus 18 over 30. And this is very simply 0.8 minus 0.6. Velocity vector is the vector that provides the direction of the motion, like this vector, like the normalized direction vector, but also provides the speed at the same time. Velocity vector is nothing else but normalized direction multiplied by speed. Actually, speed should be symbolized with these vertical lines here as a number representing the magnitude of the vector. So we have speed is 2 units per second. This is the normalized direction vector, 0.8 minus 0.6. This is equal to 1.6 minus 1.2. And this concludes question number 2. Some of you attempted a different way of finding the velocity vector, in which you took the displacement vector and divided it by time. So you got displacement vector was 24 minus 18 divided by 15, and it gives you 24 divided by 15 is 1.6, minus 18 divided by 15 is minus 1.2. As you can see, we get exactly the same result here and here, so this is perfectly fine alternative solution. But any solution in which you, and it happened quite often, you multiplied your vector by time, so 15 was a multiplier, not a number used in a division, well, totally wrong. Question 3. At your initial positions, is your enemy in front of you or behind? This is clearly a question about the dot product. The question is, at my initial position, is my enemy, which is located here, in front of me or behind? Front and behind is defined by this vector here, which may be either the displacement vector towards the beacon, or my velocity vector, which is the same direction, or also my normalized direction vector, which is also the same direction. Whichever of these three vectors you took, it was fine. If you, however, have taken my initial position minus 11, 10, it was totally wrong. Positions very rarely would make any sense in dot product calculations. Okay, so position just tell me nothing about my current direction of my motion. So where is my front, where is my rear end? Okay, so this is my position, and these three vectors, once again displacement, normalized direction, or velocity vector, are all good. How about the enemy direction? Enemy direction is defined by a vector that can be drawn like this, and this is the displacement of the enemy in relation to my current position. So this is again the relational position, relational coordinates of the enemy in relation to my current position. If you have used these coordinates directly in the dot product calculation, it also wasn't good. Right? What you need is the relational position of the enemy in regard to my current position. So let's calculate the displacement vector. Displacement vector D is my enemy position 30, 23 minus my current position to get the relative coordinates, minus 11, 10. This is pretty much straightforward calculation unless you make some mistakes with positive and negative numbers. So 30 minus 11 is the same thing as 30 plus 11, that's 41. 23 minus 10, it's simple, 13. So these are the relative coordinates of the enemy, the coordinates of this vector here. The second vector to be used in this dot product can be either displacement of the beacon, my velocity vector, or my normalized direction vector. Whichever of these three you choose is good, but I will take the normalized direction, which is 0.8 minus 0.6. And the reasons for this decision will be clear with question 6. We just will need this dot product calculation again. So we need to dot this and this. Let's do this operation in this way. 41, 13, 0.8 minus 0.6. And now we will dot these together. 41 times 0.8 is 32.8. 13 multiplied by 0.6 is 7.8, but we take the minus sign here, okay? So the result is 32.8 minus 7.8. This is 25. And this normal calculation tells us that the enemy is in front of my current position and direction. Question number 4. Write your motion formula and find your exact position after 10 seconds of flight. It's not a very difficult question, and most people got it right. This is our motion equation, so let me copy this. Position at time t equals the initial position plus vt. T stands for time, v is the velocity vector. So, in our situation, pt is equal, my initial position was minus 1110, plus I will put t forward here, and the velocity vector is the vector we have calculated in question 2. This is 1.6 minus 1.2. 1.6 minus 1.2. And that's the motion equation for myself, for my space fighter, or whatever it was, space fighter, yes. And further on, the question asks me for position after 10 seconds of flight. So it is position after 10 seconds. This will be minus 1110 plus 10 times 1.6 minus 1.2. So we get, rewrite this, minus 1110 plus 10 times 1.6, it's 16, and 10 times minus 1.2, it's minus 12. Therefore my position will be minus 11 plus 16, it is 5, 10 minus 12, it's minus 2. 5 minus 2 is the correct answer. Question number 5 seems similar. Write your enemy motion formula and find his position after 10 seconds of flight. But a small problem here is that we need to use, of course, the initial position of our enemy, which is 30.23, plus time multiplied by enemy velocity. What is the enemy velocity? To find it out, let's have a careful read of the text of the question. Your enemy initial position, he is moving in the direction that is perpendicular to your direction. If this is perpendicular to your direction, this is also perpendicular to your velocity, and twice as fast as you. So what kind of velocity it could be? It looks like my pen went out. The way to create a vector perpendicular to the given vector, and the given vector is our velocity vector, so it's 1.6 minus 1.2. First thing is to swap the two numbers, so I have minus 1.2, 1.6, and change the sign of one of these, so I have a choice between making this number negative or this number positive. Looking at the diagram, we can easily notice that if the enemy is to approach my current position, it should rather make forward towards the negative x and negative y. So I will choose this vector as its direction, some kind of a direction vector. If you have decided to use 1.2, 1.6, it would be the other way around. It would be flying this way instead of this way, but I also accepted these solutions as well, okay? But I will use this value here, minus 1.2 minus 1.6. But we also know that our enemy is flying twice as fast as you. So I need to multiply this by 2, eventually getting the velocity vector minus 2.4 minus 3.2. That's the velocity of my enemy. Therefore, it's minus 2.4 minus 3.2. That's the motion equation for my enemy. And now I just need to calculate its position after 10 seconds. This will be 3023 plus 10 seconds times minus 2.4 minus 3.2. So this is 3023 plus minus 24 minus 32. 30 minus 24, it's 6. And 24 minus 32, it's minus 9. That's the position of the enemy after 10 seconds, and this concludes the question 5. To summarize, what we did in this question 5 was to get the velocity vector of your enemy, you had to take your own velocity vector, given like this, swap x and y, and change the sign of one of these numbers to get the perpendicular vector. And if you did it by creating two negative numbers, that was very good, but if you did it by creating two positive numbers, like 1.2, 1.6, it was also considered a good solution. You also needed to multiply this velocity by 2, because the text of the question told us he's flying twice as fast as you. Next is the question 6, which proved to be very challenging for most of you. Find the coordinates at which your enemy will cross your route. And we have a hint here, he's moving on the fastest perpendicular course towards your route. If we have this properly drawn like this, it's clearly visible that enemy is flying this direction, and the meeting point, the crossing point, the point which we are due to calculate, is right here. This point is called a projection of a point towards a line, and we have a special formula for this kind of projections, and this formula is here. This calculation requires us to know the displacement vector towards the enemy position, but such a vector we have already calculated. We called it d, and it was calculated in question 3 with the value 4113. So relational position of the enemy is 4113. We also need to know the normal vector defining the direction of our position to find this projection here. Our normal vector has been calculated in question number 2, 0.8 minus 0.6. And now our projection formula, given like this, will tell us this is the point D. Let's call this thing d prime, our d prime equals, so that's the vector d prime. This vector equals d dot n, so d dot n dot product multiplied by n. This is basically what our formula for projection of a point onto a line normally tells us. We know d, we know n, we even know d dot n, because I have already done this calculation of the dot product in the question 3. Now explaining why in this question 3, having the choice between the displacement vector, velocity vector and the normal direction vector, I have chosen the normal direction vector. This is because I can reuse this calculation now. D dot n, without further calculations, I know it's 25. So, therefore, my d prime is d dot n, I know that's 25, times n, 0.8 minus 0.6, that is 25 times 0.8 is 20, and 25 times minus 0.6 is minus 15. Please take care at this moment. The coordinates we received are the coordinates, relational coordinates of the projection point in relation to my current position. These are not yet absolute positions. Therefore, to get the absolute position of this point, let's call it px or whatever, px, I need my initial position minus 11, 10, plus this calculated projection vector 20 minus 15. So this is minus 11, 10 plus 20 minus 15, and the result of this basically is minus 11 plus 20, it's 9, 10 minus 15, it's minus 5. So my crossing point, the point in which the enemy will cross my route, coordinates are 9 minus 5. Questions 7 and 8 were cancelled in this test. So as the conclusion of this recording, let's have once again a quick look at the most challenging parts in these questions. In question 1, which was the distance between the ship and beacon, the important thing was to notice that you had to find the displacement vector first, which is the relational coordinates of the beacon in relation to my current position. It's hard actually to find any real challenge in question number 2 if you only remember that speed can be found as a distance over time, that your velocity vector is always speed multiplied by your normalized direction vector, that your direction vector is normalized either velocity vector or displacement vector, that your speed can also be found as magnitude of velocity vector. Okay, this type of a question will definitely appear again in the full-time test, so you must ensure that you understand all these relations between speed, direction, velocity and the distance. In question 3, the main challenge was to remember that one of the vectors that you have to take into consideration while calculating the dot product is the relational coordinates of enemy toward the position of myself, and not the coordinates of the enemy, not the coordinates of my position. It's this vector dot this vector. A challenging part in questions 4 and 5 was the calculation of the enemy velocity vector, which had to be perpendicular to my velocity and additionally multiplied by 2. And in the question 6, once you noticed that the crossing point that you were looking for was in fact a projection of a point towards defined by my motion direction, it was just using a formula, calculating against this formula, and one more tricky point was to remember that the result you get, 20 minus 15 in this case, is just this vector here, and to find the actual position of the crossing point you have to add this vector on top of your current position to get this final result. This concludes my presentation. Thank you very much. All three of them, or actually each one of these, whichever of these three you choose is good, but I will take